this brings us to our real big part, hypothesis tests. So we actually kind of, correct me if I'm wrong, but we kind of introduced a little bit of hypothesis tests, like a z-test and such. But in this section, we're going to specifically go into it quite a lot, right? So, the first thing basically on our hypothesis test, our statistical test, we start with a hypothesis. And our hypothesis is the null hypothesis, okay? So our null hypothesis, the reason why we call it null is basically we are assuming there is no effect. So I kind of wrote this little quote in here. An experimental group is no different from like the rest of the population, since the treatment, the treatment is basically the thing that we're testing on, has no actual effect. And that's what the null hypothesis is. And our goal in a lot of ways is to test against the null hypothesis. So note, however, you'll hear the terminology, and I'll repeat this again. It's like you'll fail to reject the null hypothesis. Or you'll reject the null hypothesis. It's all about the null hypothesis. It's about the no effect part. Essentially what you're trying to do in a lot of ways, you're framing it to try to prove yourself wrong. You're trying to prove that there was no effect. Okay. This is where it's kind of like a debate, not a debate, but like how you view in science. You can only disprove things, you can't prove things. And hopefully that kind of makes sense. In the way that we talk about in science. And when we usually say we prove something in science, what we really mean is that we disproved all the other things, all the other alternatives, that it's most likely this thing is true. So, for example, it takes one example to basically disprove gravity. If we find something that completely disobeys gravity's laws and we can't explain it in that way, we could potentially essentially disprove gravity. Of course, what we do instead, because we can't find that one thing, what you do instead, you basically say, well, what if the alternative is true? What if there's some other alternative to gravity or a theory of gravity? And we test those out and we disprove it, say, oh, it doesn't work. So it turns out like what we do in science, and by extension, our statistical testing, we're trying to disprove this null. We're trying to disprove that it doesn't have, that what we're saying is true. Or hopefully that makes sense. I think I got trapped in my own words. Cool. All right. Any questions on that for like that null hypothesis, like what I mean by this? Cool. All right. And so our opposite is our alternative hypothesis. So our alternative, usually, H sub A or H sub 1. I've seen both cases, just depends who you're talking to. This is kind of assuming the opposite. So what the alternative hypothesis is assuming is the experimental group is different, and there is, since the treatment has an actual effect. Now, this is where it's really important to say, okay, what we're trying to do, we never accept the alternative hypothesis. We just say we fail to reject the null hypothesis. And I'm going to put that little extra, stringent, kind of like my thing with pie charts, is that technically you'll see people say accept the alternative hypothesis. You never accept you never accept the null hypothesis. You only reject. You either reject the null hypothesis or fail to reject. Okay, because hopefully that terminology makes sense. All right, and a quick little warning here is that these hypotheses only care about if they are significant. And significant has a very specific terminology. Significant meaning that they are in fact different, or there is an effect, but it doesn't necessarily mean there's a strong effect. Just because you have something that's clearly statistically significant doesn't mean that there's an actual important factor to it, okay? And that's a subtle difference, and we'll actually see effect size in a bit, okay? All right, any questions on hypotheses in general? Okay, so it's always important, I would say, is that you always write down your null and your alternative hypothesis before you actually perform the test. So it's important to actually have these things written down, because then basically it helps clarify what you're actually testing and what you are hoping to achieve, right? So important part is like, okay, cool, we got our hypotheses, what do we do with this now? Well, what we want to do now is say, is there an effect? And the way we determine that effect is basically from our p-value, right? So basically, we are making this hypothesis, then conducting an experiment, and we need to figure out, was there a difference between our experiment group and our control group? Okay, so this is where we use p-values. And p-values is kind of like, the way I phrase it is how strange things are if our null hypothesis is true. So we assume that there shouldn't be any weirdness kind of thing, or that we say there's no real effect, and there's other ways to explain it, but maybe things got really weird. So a point again, I think I brought this up before, is p-values with puppies. So there's a good article. There's also a good video if you don't like reading. Again, I don't know if you guys can read or not, but you can watch this video about basically she explains p-values with puppies, and essentially saying, I'll kind of summarize it going forward. But what she says, like, you've come home and you find your puppy with essentially like a garbage can over their head. And so there's a couple possibilities. One is that your puppy got into the trash can all on their own, or the other possible worlds that would still include this puppy with the trash can over their head. So one scenario she gives, like, maybe your neighbor broke in, trashed the place, and put the trash can on top of your puppy's head and snuck out the door just in time for you to like see the puppies with the thing in there. It's technically possible, but it's very, very rare. And so this p-value kind of measures in a sense like how weird would this be if this actually was true? If the null hypothesis was your puppy didn't do anything wrong, it was framed, or some other thing explains it. So this is where it's like, well, it's probably unlikely. It seems like the evidence again suggests that the puppy actually did something wrong. And this would be like a very high p-value. Okay, so this is kind of like my p-value is the weirdness, or how strange things are. Okay, so going off of that though, we have our, oh, before I say that, does everyone understand for p-value? P-value is not super understandable, but hopefully you guys understand what I mean by like weirdness. Okay, so again, it's kind of like the probability of like this happening, even though the, like, considering the null hypothesis is true. So some other weird factor just by pure chance happened instead of it actually being explained by some experiment. Okay. So this brings us to our critical value. Oh, Bardo, you had a question, I think, or I saw you on mute.
Yeah, so high p-value then, it means that the null hypothesis is probably true then?
I'm sorry, I might have misspoken. Usually when we say like the high p-value means that we can't reject the null hypothesis. Sorry, if I think I misspoke. I think I did say that. Is that, for example, the if you have a very, very low p-value, it means the low probability that the weird thing happened all on its own. So it's probably in fact an actual effect. So if it's a low p-value, we can reject the null hypothesis.
Okay.
Okay. Does that make sense?
Yep.
Yeah. Thank you for catching that. I think I did misspeak, so I'm glad that you brought that up. So this kind of leads into critical values, because our critical value now is like, okay, we get a p-value. Our p-value can be ascertained itself, but you can imagine, well, how much is too weird? So critical values, in a lot of ways, I think of it as like it measures how weird things can get, right, before we reject the null hypothesis. For example, it's like, for like the way I kind of like think of this is like if you flip a coin, and you flip a coin 100 times, and you find that the coin landed on heads 51 times and then tails 49 times. Like, well, it's like, that's not too weird. Like, that's like, it's a little bit off from 50%, but I'm okay with a little weirdness, right? In the sense that like, it might not be exact. But if you got like flipped the coin 100 times and your coin landed on heads every single time, then my null hypothesis that the coin actually has, is actually fair. It will flip 50-50. It's like, well, that's really weird. Like, that's not typical. Like, that's kind of like really out there, right? Now, technically, it's possible to flip a coin 100 times and get heads and it still be an actual fair coin. It's just by chance, it just happened to land on heads, like really lucky, right? It's just that that's so rare that it's like, well, it's probably not the coin. Something's probably wrong with this coin. And that's what our critical value is saying. It's like, at what point do you say, how much weirdness are you able to accept? 1 or 2 more head flips than tails, that's probably fine. But if you have all head flips, you're like, whoa, this is super weird. So there's kind of that threshold of like, what is our weirdness? Okay, and this is what our critical value is. And we directly compare our critical value, also called alpha, or alpha value, basically saying, when do we say something is significant? And this should be defined before you actually perform the tests. And essentially, because it doesn't really matter about, like, in a lot of ways, your definition of the critical value doesn't matter on the p-value. It really should matter about your situation. How much weirdness are you able to allow? Like, how much randomness or chance are you able to consider? Some disciplines, for example, like when I when scientists consider like particle physics, they do many, many experiments, very, very precise, is that they don't consider something significant essentially until like a very, 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 very small alpha value. And that's because they're pretty good at actually finding all these things. So if they find something happen outside of the alpha value, like equivalent to like 7 or 5 standard deviations, depending on what you're talking about, you would say, whoa, that has a significant result. If you waited for 5 standard deviations, which is like equivalent of like 0.000000001 for your alpha value, for like the medical field, you would never be able to approve any drugs because there's just too much randomness. People are different. People have different, reactions to drugs and stuff like this. There's not enough people to test that way to say like, over the trillions of people you could possibly test, like, well, there aren't a trillion people. So even if you had the whole population test them out, you couldn't determine that full significance value. So alpha really depends on your situation, not on the p-value. So that's why it's important to define it ahead of time. Okay. And so this is a little comic from XKCD. I think I might have even shown this exact one. I like XKCD, but you can see here, it's a little bit of a joke. It's that we usually talk about like, oh, really significant. We say like, oh, an alpha value is like 0.01, and this p-value is less than that. And they say significant, usually about 0.5. There's this joke, it's like usually alpha is set to about 0.05. So getting exactly 0.05 for your p-value, like, whoa, like that's really weird. We need to redo this stuff to readjust. And this is where it's something called things like p-hacking, where you might adjust your alpha value and say, hey, let me just adjust this value so it falls just underneath the p-value, right? And in that case, like, well, and that, again, you should be thinking your critical value ahead of time before you ever consider your p-value or calculate your p-value, okay? This brings us to a little warning about p-values. And I know I brought this up before. This is when, like, if you test multiple things multiple times, because the p-value is just probability. So if you test things over and over and over again, eventually you'll find a p-value or a p-value that is large enough to cross over your critical value. And then you can say it's significant, but that's because you repeat it over and over. So there's this really interesting like cautionary study where you might have heard like weight loss or chocolate is connected to weight loss. So it turns out like eating a little of chocolate, dark chocolate, or I don't know if it's dark chocolate, is connected to weight loss. And you might have even seen this. You might even like think this is true. Turns out this is a really interesting one, is that the person, John Bohannon, I think he's a PhD in biology. He actually purposely said, I'm going to make a study that is going to say, I'm going to do everything correctly, but basically he's going to test a whole bunch of things out, and whatever those things are, I'm going to publish it into this journal and essentially trick the media into showing that this is true. And he did this on purpose in the sense of saying, look how easy it is to make it seem like something is significant. And then people run wild with it. And this is his actual paper that it was technically published in this journal, but then removed. There's this whole article that explains the whole ordeal. I think does a good job at showing like what this looks like. But the important part is that for us at least, is that he tested many, many different things. He basically got a very small sample size of people. He did basically the anti-good experiment, I guess a bad experiment. But he got a very small sample size. He tested a whole bunch of things and measured a whole bunch of different stuff. So he said, oh, I'm going to give some people chocolate, some people, I'm making something, I don't remember exactly, like wine, exercise, jumping jacks, whatever. And then he measured like weight, cholesterol, blood pressure, heart rate, all these different things, and basically tried to find something that was statistically significant, even though in reality, it probably was just pure random chance. And this is where this comes from. So kind of an interesting little article, kind of cautionary tale. So like the whole moral of this is that just measuring multiple times with your p-values can give weird results. So I think I've seen this, I showed you this one exactly before, but kind of giving the scenario, it's like basically scientists come in and say jelly beans cause acne, and say, all right, we need to investigate this stuff. It's like, okay, we found no link that jelly beans and acne are connected by a p-value greater than 0.05. So the critical value basically would be 0.05. So they said, okay, well, it never crossed that threshold. P-value was bigger than that 0.05. So we show that basically acne is probably not linked to, or jelly beans are not linked to acne. But they said, oh, it's a certain color. So this is a key part. It's like, well, it's a certain color. Now, if in reality, which is probably true, jelly beans don't cause acne, you're probably not going to get a result. But if you test this over and over again, right, eventually, just like flipping that coin, right, if you flip it enough times, eventually you'll find some weirdness. Like you're like, oh, wow, I got like 20 heads in a row. Like, this is crazy. Like, how'd this happen? So this is kind of what's going on here. So what they do, they test every single color of jelly beans. And for most jelly beans, as you would expect, doesn't cause anything. But I think there's one right here. They find that their p-value is actually smaller than 0.05, and say, whoa, that means that green jelly beans actually have a connect to acne. Where in reality, if you think about this, the person who did this, XKCD again, is pretty smart. He does 20 different colors, and a p-value of 0.05 represents 5%. So 1 out of 20 times you would expect your p-value to be higher than 0.05. So only one of them was actually above 0.05. So, and then again, going to the news, taking this is statistically significant, but it's probably not what you're expecting, in the sense that this is probably not true. It's just by the fact of probability. Okay, so that's kind of giving you guys an example of, like, be careful of things. But any questions on on what we do for hypothesis, p-values? P-values are a weird one, but the main thing here is just having hypothesis tests. So you do your null and your alternative. You determine your critical value, your alpha value ahead of time, and then you calculate your p-value and compare it with your alpha. Okay. Any questions or anything going forward? Cool. All right. So this leads us into our t-tests and t-distributions.